When we talk about what are skeletons useful for, first and foremost, it acts as a lever for the body. So our attachment points, where our tendons and muscles are, provide support for the body. It protects our internal organs, our rib cage, our spine, protect our skull, naturally. They all protect things that we don't want somebody jabbing at. Without the skeletal system, we wouldn't be able to move our body. So we need our bones and our muscles to produce movement. If our tendons aren't attached to muscles, we're not going to be able to move. It stores minerals, especially calcium and phosphorus. So if you're not getting calcium in your diet, but you did before, it'll actually be extracted from your bones and then used in different cells around the body. For me, it forms blood cells, so there's red marrow found throughout bone cavities, spongy bone, and a lot of different bones. And we'll talk about what spongy bone is in a little bit, but basically, not all bones are the same. Part of the bone is used to form red marrow. And then there's also yellow bone marrow, which stores fat cells, once again, for, because, hey, we didn't always have Amazon delivering. So, first off, are bone cells alive? Yes, they are. So, the cells in your bone consume energy using cellular respiration. They grow and repair themselves, and the amount of calcium in the hard part of the bone is regulated by our hormones. The bone marrow, the interior of the bones, where we make red blood cells and lymphocytes. And then we've got the periosteum, which is a protective membrane layer that surrounds the bones, containing nerves and blood vessels. And that's what keeps the bones moist and aids in repair. So from last unit when we talked about bones having a greasy feeling, that's the periosteum that you would be feeling on the outside of the bone. Osteoclasts are specialized cells that create enzymes that dissolve the bone. So there's osteoblasts creating the bone, osteoclasts dissolving the bone. And they will reshape the bones as they grow, remove any cellular waste or debris that is needed to be removed, and they help repair broken bones. They maintain the calcium homeostasis in blood, so basically the calcium levels in your blood. If you need more calcium, bones dissolved, like we said earlier. So if you don't have enough calcium in your diet, it can lead to osteoporosis, just like I talked about, which is a weakening of the bone. Basically, osteo is relating to the bone. Porosis is you've got porous bones. You don't want that. Here's two pictures of what the arrangement of bone cells look like. So The one on the upper right is a cross section, kind of a horizontal cross section, and then the bottom left is a vertical cross section. So the dark black circles here correspond to the kind of things that look kind of like rivers down in the other one. So those black sections are called Haversian canals, and they're surrounded by lacunae, which are rings of osteocytes. How many bones does a person have? So, a common question, and the answer is 206, right? No. 206 bones in an adult. But when you're born, 200 or 450 bones in a baby that are going to fuse together as that person develops. If you were born with 206 bones, your mom wouldn't like you as much as she does now. So here's an x-ray of a newborn baby, and you can see the white portions are where there's bone tissue, and then the dark blue is going to be those gaps there indicate where there's cartilage. So that cartilage is going to get filled in, and these. So here's a look at how a femur changes as a person ages. So we've got straight cartilage on the left, and then as we go over to the right, we've got more and more bone tissue forming until we have an adult bone, which has no cartilage in it. Here's a look at the spongy tissue in the head of an adult femur, and then we've also got compact bone and spongy tissue in the bone of in a skull bone. So when we talk about bone, bone has a dense organic matrix. So living osteons, so osteocytes, osteoblasts, osteoclasts, and blood vessels, as well as inorganic minerals, calcium, phosphorus, potassium. And we've got several different parts. So going top to bottom here, we've got the epiphyseal plate, which is your growth plate, the spongy bone, the compact bone, medullary cavity, yellow marrow, and then on the very outside is the periosteum. So the epiphysis is the ends of a long bone. So that's going to be, and we'll talk about what long bones are in just a second. The diaphysis is the weight-bearing portion, so the compact bone. And then the epiphyseal plate is where the epiphysis and diaphysis connect, and that's your growth plate. When that growth plate ends, then you basically stop growing. So some people who've had x-rays, the doctor will estimate their final height by taking a look at their epiphyseal plate. We've also got spongy bone, which has, like we saw before, a lot of spaces, and it's full of red marrow normally. So think of it as a sponge full of basically cells that are going to be creating red blood cells. Then there's compact bone. So compact bone is the region of the bone that's very dense. Yellow marrow is fat storage, and then the red marrow is where the red blood cell is produced. In between our bones, we've got the joint. So the joint is going to be where the two bones meet. And then there's going to be three different types of connective tissue there. You've got the cartilage, which wraps the ends of the bones to prevent scraping. So, in older people. So my father needed a total knee replacement, basically because he had worn down the cartilage in the ends of his tibia and his femur, and it was just bone on bone, and walking was very painful. We've got ligaments, so ligaments connect to bones. So, hey, remember that time that I was gone for a week because I had to get a new ACL? Well, without it, I was having a lot of trouble walking because, well, my bones weren't connected as they should have been. And then we've got tendons. So tendons connect muscles to bone. So the most notable one is the Achilles tendon in the back of your ankle. So basically, if you pull or if you rupture or, otherwise injure your Achilles tendon, your calf muscles are no longer connected to the back of your heel, and you won't be able to raise your, use your calf muscles to raise your foot. That's a very bad injury. So bones can tell us a great deal. Sometimes we refer to it as an osteobiography, so the biography of the bones. And, paleoanthropologists take a look at the bones of human remains from eons ago, and they can find times that, food was more scarce because there's growth rings in the bones, just like there's growth rings in a tree. We can also figure out things like handedness. So the bones in the hand that's used more are going to be slightly larger. We can figure out how active that person was. If there's more wear on the bones and the bones are sized bigger, there's basically more physical activity. We can talk about health and nutrition, so the bone density, how much calcium there is, teeth, arthritis. For forensic analysis, we want to look at the age of the skeletal remains. So, are the bones completely fused? What's the bone density like? If we have the pelvis, the skull, and sometimes the femur, we can determine sex. If we have long bones, which we're still going to talk about, we can estimate the height. We can use the skull characteristics to get an idea about the possible race. So, I keep talking about long bones. So we've got to break up the bones into different categories real quick. So the long bones are, check this, longer than they are wide. We've got a long diaphysis, a long shaft with bulky ends. They're primarily compact, but there's spongy tissue at the end of those bones. And we can use this to extract height and the general frame size from these bones. Examples of long bones are going to be the bones of the arms and legs and some of the phalanges. So femur, tibia, fibula, humerus, radius, ulna, those are all going to be considered long bones. The short bones are cube-shaped, wider than they are long a lot of times. The tarsals, the carpals, the patella, these would all be considered short bones. So if we get wrist bones or ankle bones, those would be the short bones. Irregular bones are thin, flat, curved. They're mainly spongy tissue. So the vertebrae, mandible, the hyoid, so the hyoid is in your throat, sacrum, coccyx, those would all be considered irregular bones. And then the flat bones. So flat bones are mainly spongy bones with a thin layer of compact. So the skull plates, the sternum, scapular ribs, and the ilium. So the ilium are kind of the sides of your pelvis. So those would all be considered flat bones. We can also determine whether bones are human versus non-human. So, a human's tibia and fibula and radius and ulna are separate bones. Animal bones are denser and less porous when viewed as a cross-section. Animal femurs are usually about the same length as the other limbs, so when you think about it, humans have longer legs than arms. Humans have 4 curves to the spine. Animal spines are much more straighter because animal spines are usually meant to run horizontally, not vertically like a human's. Animal jaws are generally V-shaped, whereas humans, it's more of a U-shape. And then humans have flat teeth, animals have fewer teeth, larger canines. So if you're sitting at home watching this with your dog or your cat, pry open their mouth if they're friendly. If your dog has a history of not being into that, then don't. Hey, these bones aren't human bones. They're actually the back leg of a black bear. Now, when you find that out, like you go like, oh, well, yeah, because the leg bones here are disproportionate to the size of the foot. But if I found these out in the woods, I'd be like, ooh, geez, 911. And I think most first responders would be like, oh, geez. But at the end of the day, it's just a black bear, which I'd still be pretty concerned about if I found that out in my backyard. Okay, that's it for today.